So this will be the lecture over section 27.8. This will be the last one in this chapter. We're going to look at relativity and Newtonian mechanics again. The special relativity, special theory of relativity is a generalization of Newtonian mechanics. All the principles of Newtonian mechanics are present as limiting cases when all the speeds are small in comparison to c. Further generalization to include accelerated frames of reference and the relationship to gravitational fields leads to the general theory of relativity. So obviously you got a lot of changes that relativity requires out of Newtonian mechanics. These include length, time, equations of motion, conservation of energy, of momentum, that kind of thing. So, in a sense, you've really kind of taken Newtonian formulations and changed it around. But what you've also tried to do is try to make sure that whenever things are moving at very slow speeds relative to the speed of light, that you still get the same results, and that's what's been accomplished here. So Newton's laws aren't necessarily wrong; they're just simply incomplete, and it's just simply because this is not something that we've observed here. We've had to get in and to really focus in on what light is in order to be able to make these kinds of relativistic deductions. So, is this the final word on whether or not things might change from here on? Inertial frames of reference have occupied a privileged position in our discussions. Should the principle of relativity be extended to non-inertial frames? So let's say you've got a student standing in an elevator like this. The elevator cable, all of them are broken, and the safety devices have all failed. So you're in for a good spot of luck there. So the elevator's in free fall. Obviously, acceleration is 9.8 meters per second squared. Losing her composure, the student loses her grasp of her physics textbook, which of course she would have in an elevator in this situation. The book doesn't fall to the floor because the student and the elevator all have the same free fall acceleration, but the student can view the situation in two ways. Is the elevator really in free fall, which obviously is what you'd be thinking about if you're plummeting to your death, with her in it, or is it possible that somehow the Earth's gravitational attraction has suddenly vanished? As long as the student remains in the elevator and remains in free fall, can't tell the difference. A more realistic illustration is an astronaut in a space station in orbit around the Earth. Objects in the spaceship seem to be weightless because both they and the station are in circular or elliptical orbits and are constantly accelerating towards the Earth. But without looking outside the ship, the astronauts have no way to determine whether gravitational interactions have disappeared or whether the spaceship is in a non-inertial reference frame, accelerating towards the Earth. So these considerations are basically what you're using with Einstein's general theory of relativity. If you can't distinguish experimentally between a gravitational field at a particular location and an accelerated reference frame, then there can't be any real distinction between the two. Pursuing this concept, we may try to represent any gravitational field in terms of special characteristics of the coordinate system. So this turns out to require even more sweeping revisions of space and time than did the special theory of relativity, and we find, in fact, in general, that the geometric properties of space are non-Euclidean, and gravitational fields are closely related to the geometry of space. So in other words, gravity is going to warp how we perceive things. The general theory has passed several experimental tests. One test has to do with the understanding of the rotation of the axes of the planet Mercury's elliptical orbit, called the precession of the perihelion of Mercury. Perihelion, of course, being the closest point as it approaches the sun. Another test concerns the apparent bending of light rays from distant stars when they pass near the sun. And the third is gravitational redshift, the increase in wavelength of light proceeding outward from a massive source. Some details of the general theory are more difficult to test, so they remain speculative in nature. But this theory has played a central role in cosmological investigations of the structure of the universe, formulation and evolution of the stars and related matter. So this theory is pretty complicated. It's not something we're going to get into very much, but it's out there. And yes, it is an extension of special relativity. So I hope you've enjoyed these lectures.